What if I told you there is a speed in this universe faster than the speed of light? Not a rumor, not a sci-fi theory, an actual, laboratory-tested, Nobel Prize winning discovery. And the crazy part? The man who first warned us about it, Einstein, spent the last years of his life trying to prove it was impossible. Let's rewind. You've probably heard that nothing can travel faster than light. It's one of those facts that feels as solid as gravity. But in 1935, Einstein himself cracked that foundation, not intentionally, and not because he wanted to. He was actually trying to prove that quantum mechanics was broken. Here's the setup. Imagine you've got two particles, let's call them twins. You fire them in opposite directions. They fly apart, maybe light years apart. Then you measure one of them. The instant you do, you instantly know something about the other one, not because someone sent a message, but because they were created together and share some kind of deep, unbreakable connection. Einstein called this spooky action at a distance. He hated it. To him, it meant quantum mechanics was broken because this connection seemed to work faster than light. But nobody really cared. Einstein was 56 at the time. Most physicists assumed he was just an old man uncomfortable with the new, weird world of quantum physics. His paper gathered dust for nearly 30 years. And then, a young physicist named John Bell pulled it off the shelf and changed everything. Bell had what looked like a simple idea. He said, okay, if Einstein is wrong and these particles aren't secretly communicating faster than light, then their behavior should follow certain mathematical rules, specific limits on how correlated their results can be. He turned Einstein's philosophical complaint into an actual math problem that could be tested in a real experiment. That paper, written in 1964, is now considered one of the most important in the history of physics. Fast forward to the 1970s. Scientists built the experiments. They fired particles apart, measured them, and checked the numbers. And the numbers broke Bell's limits, completely and consistently. The results were so correlated, so perfectly linked across huge distances that there was no mathematical way to explain it without some kind of influence traveling faster than light. Einstein's spooky action was real. Now here's where it gets even weirder, and this is the part that most science videos skip past. Why doesn't this break everything? If particles can influence each other faster than light, why can't we use that to send a message back in time or cause some catastrophic paradox? Let me explain with a quick story. Imagine you and your friend each get one of these entangled particles. You're on opposite sides of the planet. You measure yours. You get a result, let's say, plus. Your friend measures theirs at the exact same moment and gets minus. Perfect correlation, instant, across the entire Earth. But here's the catch. Your result was completely random. You had no control over whether you got plus or minus. And because it's random, you can't encode a message in it. You can't send information. You can't exploit the connection. Nature figured out the perfect loophole. So quantum mechanics is technically non-local, meaning stuff can influence other stuff instantly across any distance. But it's non-local in a very specific, locked-down way that prevents you from doing anything useful with it, at least for now. But here's the real philosophical earthquake that scientists are still arguing about. If these particles really do influence each other faster than light, what is actually going on? There are two major camps, and they've been at war for almost a century. The first camp is called the Copenhagen interpretation. Think of it as the don't ask school of physics. The idea is basically, the particle doesn't have a real state until you look at it. Before you measure it, it's in a superposition, kind of both things at once. Like a coin spinning in the air that isn't heads or tails yet. When you measure it, the wave function collapses, and you get a definite answer. Where does it collapse? Instantly, everywhere. That's your faster-than-light influence. The Copenhagen crowd says, don't worry about what's really happening under the hood. Just trust the math, predict your measurements, go home. Niels Bohr, the godfather of this view, literally said, the job of physics is not to tell us how nature is, just to predict what we'll observe. Einstein despised this answer. He said it was a tranquilizing philosophy, a way of putting people to sleep so they'd stop asking real questions. He believed there had to be something deeper going on. He thought particles had real, definite states all along. We just didn't know them yet. Like hidden variables, like a coin that's already heads. You just haven't looked. Bell's theorem showed that hidden variable theories in their simple, local form can't work. The correlations are just too strong to be explained that way. But here's the twist. There is a hidden variable theory that does work if you allow it to be non-local. It's called Bohmian mechanics, or pilot wave theory, and it's supported by a growing minority of physicists. In this view, particles have real positions at all times. guided by an invisible wave that tells them where to go. And yes, this wave can act non-locally. It's weird, but it's consistent. Then there's the third option, and this one is the most mind-bending of all. What if there is no collapse? What if every time a quantum measurement happens, the universe doesn't pick one outcome, it picks all of them? Every possibility branches off into a parallel universe. You measure your particle, and in one branch you get plus, and in another branch you get minus. And both of those versions of you are equally real. This is the many-worlds interpretation. And the wild thing about it is that in many worlds, there is no faster-than-light influence. Your particle doesn't need to tell the other particle what answer to give. Both particles already have both answers, they're just in different branches. In many worlds, Einstein's dream of a local universe where nothing influences anything else faster than light actually survives. The price you pay is infinite parallel universes constantly branching. Some physicists think that's fine, some think it's insane. The debate rages on. And why does this all matter beyond being a great pub argument? Because the question of locality, whether physics is local or not, is at the heart of one of the biggest unsolved problems in science. We have two great theories: quantum mechanics, which describes the world of the very small, and general relativity, which describes gravity and the large-scale structure of the universe. They're both extraordinarily accurate, and they fundamentally don't agree with each other. Physicists have been trying to unite them for decades. Every attempt has hit walls, and some researchers now suspect the reason is exactly this. We've been trying to stitch together relativity, which is deeply, fundamentally local, with quantum mechanics, which, in most interpretations, is not. If many worlds is right, and quantum mechanics turns out to be local after all, maybe that opens the door. Maybe a theory of quantum gravity becomes possible. Maybe Einstein wasn't as wrong as everyone thought. Let's zoom back out and think about what we actually know. In 2022, the Nobel Prize in Physics was awarded to three scientists: Alain Aspect, John Clauser, and Anton Zeilinger for their experimental work on entanglement and Bell's theorem. The Nobel Committee said their work demonstrated violations of Bell inequalities and pioneered quantum information science. In plain English, they proved that quantum particles really are connected in this instant, faster-than-light way. It's not philosophy anymore. It's Nobel-winning experimental fact. So what are we left with? A universe that is, at its deepest level, fundamentally weird. A universe where two particles can be separated by the entire width of a galaxy, and measuring one of them instantly determines something about the other. A universe where the speed of light is the speed limit for everything we can control, but not for the strange, ghostly connections between quantum states. A universe where the greatest minds in history, Einstein, Bohr, Bell, fought for decades over what it all means, and we're still not sure who won. John Bell died in 1990, just months after giving a talk in which he said, "I think you're stuck with non-locality." I don't know any conception of locality that works with quantum mechanics. That was basically his last word on the subject. And here we are, 35 years later, with a Nobel Prize confirming he was right about the problem and still no consensus on the solution. So the next time someone tells you the speed of light is the ultimate speed limit, you can smile and say, kind of. Technically, yes. In practice, for everything we can control, yes. But underneath the surface of reality and the quantum fabric of the universe, something is going on that Einstein called spooky, that Bell proved is real, and that we still don't fully understand. And that might be the most honest thing physics has ever told us. The universe is stranger than we thought, stranger than we can think, and it's been waiting 90 years for us to catch up.